All right. Zoom actually decided to work today, so we'll go ahead and have this recording if you want to refer to it later. If you don't know, I plan on sharing my online course too. That was one of the reasons I decided, since I got it to work, to go ahead and try to use it. So I clear with everyone. As we go into today, though, we want to continue with our discussion with relations. All right, but we're going to make a little bit of a transition today, going from relations in general to a specific group of relations. Now, the reason we want to do this is you're going to find we're trying to make it a little bit easier to work with, is what we're going to end up trying to do. Okay. So I have a graph up here that represents a relation. We know it's a relation, as we discussed, is we have that graph that I've drawn as a blue line. The reason we have the line drawn is because there's an infinite number of ordered pairs. That's the main thing we want to take from that. What do we do to identify the domain? So we're looking at this graph. We want to identify the domain. And we use the x-axis, right? That was one of those things. Reading the x-axis, going from the left all the way to the right. Does the graph ever stop? No. Right? Does it look like it would ever stop going left or right? There's no place where there's a solid dot open circle, right? That say don't go past this, right? And if you see it going at an angle, we're going to assume that means it's going left and down. It just means it's probably going down faster than it's left, right? Left. With that said, then what's the way that we write that? So we're all good with that. All we're taking.
So I have a question. So because of the dots being at -1 and 3, that don't mean it stopped there because of how the.
It's all about the line itself, right?
Okay.
Why did I put those dots there?
That's our point.
So, but we look at these points, there's a reason I made sure to highlight those. What's special about those?
They're equal. They're
X intercepts, right? What did I ask us to identify those?
yeah.
Now, technically, I shouldn't have to do that. Plus, it helped me graph it. That's another reason they're there. But I left them there because I wanted to make sure to be like, hey, these represent something special.
Okay.
Now, I could have done it for this one too,
Right.
but that value isn't unmeasured.
Right.
So that's why you see I focus on X intercepts.
Okay.
Why did I leave this one out? What's special about this one? It's the vertex, right? That's one thing we're going to make sure we work on when we see quadratics. Hey, that's the vertex, but what does it represent about the relation right now?
Oh,
There's symmetry there, and we're going to go in more detail about the symmetry too. Where is it at in relation to all the other ordered pairs? It's at the top, right? So make sure you remember that represents kind of like a maximum part of our graph, right? Now, we understand when we say that we're talking in just kind of simple terms. Mathematically, you have what we call relative min-max and absolute min-max. Okay, for this one, there's absolutely nothing above this point, and both sides of the graph are going where? They're both going down, right? So we can conclude that that is the absolute max.
Okay.
Right? How do we write that though? That comes the next question. Well, if we ask for the domain, the next step is probably going to be the range. Where do I start with my range? Right. So make sure again, we're starting at the bottom and working our way up and seeing, hey, I don't go past this. Right. But that bottom, as mentioned, is going to be negative infinity. What's that maximum value? Right. Why is the bracket important, y'all? It's included as a point, though. Is everyone comfortable with that?
yeah, that's why I was asking why they didn't say the domain was.
Wait, okay, state that one more time. I'm sorry.
That's why I was asking why we didn't say that the domain starts at -1 and stops at +3 because.
What about these parts though? Right? This is the entire graph.
Yeah.
The difference is this is at a place where the graph turns.
Okay.
We'll call that a turning point.
Okay.
That's the big difference. Now, where will we see stuff like this? Do you remember where this one came from? What looked like this? The square root, right? We're kind of looking at that would be one to be like, okay, that point represents something I need to stop on. There's no other movement anywhere from this. It was just this one line.
Okay.
Now, we also have some piecewise functions we talk about, we'll see kind of similar, but that's a special function when we see.
Okay.
All right. Do we all feel okay then with the domain and range? All right, so the next thing I said, identify the intervals where the relation is increasing or decreasing. So this, we kind of talked about that average rate of change, right? And I kind of went over it quickly, just kind of this idea. If I pick a point here and I pick a point here, as we go from left to right, does it go up or go down?
Okay.
Goes up, right? So for these 2 points, we see a positive rate of change, right? Which means that that would be considered increasing. Now, is that true for every point on this graph though? Oh, all I have to do is come over here and say, let's pick these 2 points, right? As we go from left to right, all of a sudden now we see, hey, it's got to go down. So what should we call it there? Decreasing, right? So what we're seeing here is that as we go through a graph, it's not always going to be one thing. So we have to be able to identify where the changes occur, right? So one thing to look for is we talked about, hey, there might be some points that we call like a turning point message, kind of just being simple about it. But what I want you to see is as we go through our graph, the left side here goes up to that maximum value, but then the right side goes from the maximum value downwards. Okay. All focused again on this point here. So if it's going up, we want to correlate that with increasing. If it's going down, we want to correlate that with decreasing. However, in doing this, we have to remember we're working with ordered pairs. Okay, so the way that we handle that is we focus on describing the X values and allow the word to tell us what's happening. Increasing tells us that our Y values are getting bigger. Decreasing is telling me that my Y values are getting smaller. So as I start at negative infinity and I work my way through the graph, it's doing it to me again, y'all. As I work my way through this graph, I have to stop here because all of a sudden now we have a different situation. But that interval that I just highlighted, negative infinity up to positive 1, is where we'll say, hey, this graph is increasing during that time. Now, what did I put on the one that's a little different? Parentheses, right? Now, the reason we want to put a parenthesis at that point, as we've kind of discussed already now, is 1, 2. If you try to do the average rate of change on a single point, that would be y2 minus y1 all over x2 minus x1. What does 2 minus 2 all over 1 minus 1 give us? Does not give us 1. It doesn't give 0. It gives us 0 over 0. Are we allowed to divide by 0? So does that mean anything to us? That's an undefined situation. It doesn't mean anything to us. All right, it's useless basically for what we're trying to do. So that's why we put the parenthesis on the 1. Okay. Now remember, this formula it's just an average rate of change. How do my Y values behave as I go through my X values? Okay. Now, with that said, make sure you see there, you can't put the same point into the average rate of change twice. It will not work. So that's why we're putting parentheses there. Now, keep in mind, this graph, as someone mentioned, has symmetry. So the other one here should be 1 to infinity to show that symmetry. But you can also just go through and continue your tracing as we just did, starting back up where we left off, and we go all the way through positive infinity, and that graph is going to continue to go downwards. Questions I clear for that one?
Okay, so why was it negative infinity to 1 and not negative 1?
Well, where is the vertex piece at that maximum value? Where does it occur at?
Okay, okay, so we're going to the, okay.
Yeah, we got to go to that maximum value, right? So it's not about the number, it's about where the point is. So remember, our focus was this point here. And are you comfortable with recognizing that means my maximum value is 2?
Yes.
Well, the maximum value is 2 occurs at
1,
positive 1, yeah. So I'm trying to put that, this is the way we kind of highlighted yesterday.
Yeah.
But this is special because what type of graph is this?
a quadratic.
quadratic, right? So that's why we can see the symmetry taking place. Hopefully, if you didn't catch on to that, make sure we're practicing that. When I look at this, hey, I can tell that's from a quadratic because we did that, right? Now, as mentioned, though, we did already kind of highlight the next two things. What did I ask here is x-intercepts, right? So what were those two guys? Now, this is a place where I can see writing as such. The curly bracket, that's just representing what we call set notation. So the two numbers here that are important are -1 and 3. Now, the reason we're okay here just stating -1 and 3 is because x-intercept is already defined. That's what we're identifying here is x-intercepts. Meaning it's understood then that both those values come from this. Whether you write it as ordered pairs or not. Now, the key here, if you remember what I mentioned yesterday, be careful on the homework. All right. There are some problems, especially those assignments I gave us for Monday, that the way they want you to type it in might be different than say some of the ones that Pearson had. Keep that in mind that you go between them and always read what it's asking you to type in. If it says put in ordered pairs, make sure you put as ordered pair. Okay. Questions with this one? All right, let's finish the one that we started yesterday. All right, hopefully we should already have this one written down from yesterday. If you weren't here yesterday, make sure you copy it down. If I remember right, we had already said the domain was all real numbers. But this one had kind of a minimal value. It's a little different though, because it has that flat portion there, right? Where we would call it constant. But that minimal value is still -6. Any concerns where I'm getting these intervals from? All right, so just to make sure to highlight, remember, as far as like say, talk about the range, I look at my graph. This is the lowest it goes, and then it goes up from there. So I start with the lowest value, -6, and I work my way up to positive infinity. What are the intercepts for this one?
Oh, no. Yeah.
All right, so be careful here. How did I word this one differently? This is an example. We have to be careful. The previous one I said to find what? X-intercepts, right? This one I said to find just intercepts in general. So what that means is I want to go through and find not only my x-intercepts, but also my y-intercepts. Okay, which means that since they want all of them, the best pattern to handle here is just write them in ordered pairs. So we'd say, hey, -6, 0, 6, 0, and what? 0, -6. Now, the reason we want to use ordered pairs here is to distinguish which ones are x-intercepts and which one is the y-intercept. We okay with that so far? Any questions or concerns? At the board open team, we can change up how we ask these, right? The way I ask on the test will not be the same way they ask it on the final exam, right? So make sure you always read what does it want or what is it asking for. Instead of x-intercepts or intercepts in general, we can be like, hey, what's the y-intercept? All right, so keep that in mind. The last question, though, I focused on that behavior, right? What's the behavior of this relation we're working with? And specifically, where is it decreasing at? So is it always decreasing? What's part of this that you see that's not decreasing? All right, so one side, specifically the right side, is increasing, right? What are we saying? Yes, all right. What did I say this was called just now going through here? So as we kind of highlight this would be increasing. And what say? Well, this one's a tough one. It is that would give us our minimum value, but be careful because there's a lot of x values there, right? This is a special situation that we call a constant. the average rate of change would be constant. Okay. What number do you think that means? And if it's constant, what number represents the change taking place? If negative goes with decreasing, right? Positive goes with increasing. So what's that leave? It'll be zero, right? So understand that, oh, hey, the average rate of change here is zero. Okay. With that said, though, are we all good then seeing that leaves us with this one side being the part that we're looking for? Where does it change though from that decreasing to constant? That's the next thing you gotta identify. Hopefully what you're seeing here, that change occurs at a particular point, right? Now, do I need the -6 though? That's the next question we have to deal with, right? Hey, the -3, -6 is our focus. Okay, because it went from decreasing to constant right there. But remember, we don't need to worry about the y value because it's already covered. So we would say, hey, this is going to be -infinity, -3. And why did I put a parenthesis here again? What is that referring to? But it's, are we solving inequalities right now? Well, no, right? So we have to be careful. Their inequalities kind of play a role here, right? We could write this as x less than -3. That is true. But was it because we didn't have equal sign, right? Well, right now we're picking whether it's there. This is the tough part we have to remember. Okay. And this goes back to what we just talked about. If I try to take a single point, as I mentioned, -3, -6, can I put that point into the average rate of change twice? No, because if I try to do it, what will it give us again? Not 0, but 0 over 0, and I can't do anything, right? So make sure you go back to that, hey, the parentheses here, because I can't plug a point in to the average rate change. I have to have two different points, okay? So we okay with this though, kind of just changing up with the different relation here? Now be prepared, because I can throw all kinds of different graphs on there right at this point where anything can happen. Okay. So here's 3 different ones we can look at. Hopefully one of them you look at and recognize it's a circle, right? What's the blue one look like it could be? Possibly a quadratic, right? What in the world's going on in the middle? A lot, right? But that's where you'll see that we can have all kinds of different things that we can put together, okay? But the key is we should still be able to read what we need to, okay? So here I wanted to just identify the domain and then determine if the relations are functions. This is where we're going to start our transition from a relation to a specific group called function. Now, with that said, there's still relations because they're a set of ordered pair, right? So it's very important. Just remember, relations, sets of ordered pairs. That's all a relation is. When it comes to dealing with this, functions are a specific group of relations that make things a little bit easier to work with. Now, all of the things here are meant to be infinities or integers. So like when you're doing the domain, if it's not infinity, it should be an integer value. So what would someone put for the first one as far as the blue graph is concerned is for the domain? So is everyone comfortable with all real numbers there? Now, do I have to put an arrow on both sides for it to mean it's going to keep on going there forever? No. So what we watch for again is that solid point at the end of the line, right? That is our main thing to watch for. So here we can definitely do that and conclude. All right. Would you agree that the next one is also all real numbers? Yes. Okay. But the circle, that one's definitely not all real numbers, right? Because the line comes back to where it started from, no matter where we kind of pick to start, right? What is the smallest x value we can use there? And we're going to assume that's what it is because I want it to be integers, okay? The biggest value though is what? 1, right? What should I put on those?
Brackets.
brackets. Okay, here we would use brackets. We're gonna assume that that point's there. And the way I drew it, I intend for that to happen. Okay. Now, at this point, we've seen some different types of domains. Keep in mind, like we saw here, we should always expect something that possibly looks like a number going to infinity as an option. But as you see here with this circle, be prepared for, hey, everything's contained within that window. It's still an infinite number of ordered pairs. Just happens to be they form a circle when we draw it out. Okay. Now, the next thing, though, I said is let's determine if the relations are functions. But what does my hint say? Is there one y value for every x value?
Yes.
Okay. So with that said, this is where we make the distinction. A function, first and foremost, is a relation, the set of ordered pairs, such that for each input, there's exactly one output. So if we pick one of these graphs and we said, let x equal -1. How many ordered pairs should I have if there's only one output? Only one, right? So let's check it, right? Let's take one of those dotted lines and just go through each one and check it. Let's use +1. Then -1. I kind of didn't consider this first one. All right, so looking over here, how many ordered pairs do we have for this particular graph? At x equal to 1. Just going to be the one where it intersects, right? Does everyone see that? Now, let's just kind of look at that though. If I take this and move it around, is there any place where it'll hit twice? So does everyone see here that we're able to just use a vertical line to kind of do a quick check? What do you have in your hand right now that can be used as a vertical line real fast? Pencil, right? Has anyone ever heard of the pencil test before? Right, that's kind of what we're doing here. But what we would say is, hey, by the vertical line test or by the VLT, this particular graph, I'm just going to put it because of space. Right, we can conclude that that's true though. That's the nice thing about that. We can definitely conclude this is true. So we know quadratics are what?
Function.
Quadratics are functions, right? And really we can look at this. Every quadratic is a function. Okay. Well, what if we take this one and look at this one? It's not a quadratic, it's something way different, a little bit more going on. What would you conclude with this one as I move this through the graph? Right, so you're saying it's a function because it will never do what? Cross it twice. Right now, once you hit twice, it's done. If it hits more than twice, no big deal. But also remember, all it has to do is one time. If you could find one place where it hits the graph twice, it fails the vertical line test. Okay. Now, the vertical line test is just a visual way to apply the definition that for each x, there's only one y. That's the key. So make sure you see here that we would continue with this by saying, hey, by the vertical line test, it is a function. Okay, just like we did before. Fine, but make sure we go back to the definition. I want to highlight to you visually that, hey, for each x, which is why the vertical line is helpful, it highlights a single x value, right? It only touches the graph one time, which means a single ordered pair is connected to that x. Okay. However, with this circle, once I move it anywhere within the circle, what do we run into? It's twice, right? Now, if we pick 1 or -5, it's only going to hit once. But remember, we're not worried about that. Once we find one place where we could say, hey, it hit twice, we would go over then and say, hey, the same statement by the vertical line test, the relation is not a function. All right, the key being all of a sudden now we're saying it's not a function. Does that mean it's useless? Just means it doesn't follow that definition, right? Then it goes back to the square root of 25. What is the square root of 25? 5. Does that mean the negative 5 is no longer needed? No, right? Remember when we talked about solving equations, right? Negative 5 squared is still 25, right? So we still have to bring it in at some point, but sometimes we have definitions that limit stuff to make it easier to work with. Okay. Any questions with what I mean by a function from a graph perspective? All right, so here's another situation then. If I gave you this equation, and I said, hey, let's graph it. All right. We can go in and start plugging in values. Let's plug in -1, 0, and 1. Okay. So I'll build a little chart over here real quick. I'm going to do -1, 0, and 1 just to get it done. All right. What type of relation is this, by the way? All right, make sure we're comfortable recognizing it's linear. As I go through with this, if we plug in 0, we get the constant term. But if I plug in 1, 2 minus 3 is what we get. If you plug in -1, -2 minus 3 is what we get. So I get a graph that looks something like this. All right. Hopefully you see there for linears, domains, all real numbers. We have that confirmed. This particular one, the range is also all real numbers. Is it increasing or decreasing?
Increasing.
It's increasing, but hopefully you see here, it's always increasing, right? So linears will have that like, hey, the increase is for the whole domain. Okay. But what we just added was the fact that, hey, there's one more step that we can do to look at this. We know it's a relation because we have X and Y, right? But this relation is special because if I take that vertical line, we can confirm. Why is it not letting me do it? We can confirm that, hey, look at that. It passes that vertical line test no matter where I put that line in. So this relation is a function. All right. We comfortable with what I did there? I was graphing it. We're getting to that conclusion. Now, the way we handle this now is to say, hey, let's have a helpful way of writing this. So we don't have to go and graph something to check if it's a function every time. Okay. The way that we change this is say, instead of writing y, we're going to write f of x. So the way that you need to interpret that, though, is it's a function that we just named f. The f represents the name of the function. And the x is the input. So like you see here, it's the function f with an input of x. Okay, it is not multiplication. This is notation. That's one important thing we want to see here. The f parentheses x stays together at all times. Now, this is helpful because it's going to help us do two things. Now that we know this is a function, I can rewrite it as f of x equal to 2x minus 3. Now, did the y disappear?
No, because y is equal.
Y is f of x, right? So keep that in mind. It's like if you see I, we didn't get rid of the square root of -1. We just covered it up with the letter I, right? And that's kind of what we're doing here. That f of x is my y value. Okay. Now, the reason we like function notation, again, first of all, we know this is a function. Whenever I plug something in, how many numbers do I expect to get back? So if I come over here and say, hey, let's go find f of 3. I just said x is 3, right? How many numbers am I going to get when I evaluate it? Just one, right? You should know that right away, though. Hey, this is a function. When I plug in 3 for x, I'm only getting one thing back. So when we do that, gives us what? 6 minus 3, which is 3. So we find that, hey, if X is 3, Y is also 3, which if we go back, we can check that, I believe, with our graph here, and then, hey, look at that. Agrees with what we had. Okay. So it's definitely helpful in that regard. All right, so let's practice using it. Here's a function, write down the function and work out those 4 problems for me. Finish writing them down and working them out. Make sure you remind yourself that the way I have that written, what I'm giving you is the X value and telling you to plug that X value into that function. So you see G of 5, like, hey, my function I have here is G of X, and I want to plug in 5 for that X side. Keep that in mind. All right, so would we agree if I wrote this out for the first one? Now, what did I put around my 5 every time I plugged it in? Parentheses. I think it's very important. First and foremost, like that first one's squared, right? But we also need to make sure when we see 7 exit, that's multiplication. Right, so that's why we keep that. And did we get -7 when we did that? No. So at that point, what we have here is what G of 5 equals -7. Now remember, that's also an ordered pair that we found here. But this is a situation where, hey, this notation actually covers the ordered pair for me. Right, it's another great thing about having that notation. Now, with that said, though, we can go on to this next one now. If we get 11 from this one would be my question. What do you think you have to be careful of in this one?
The negative.
The negatives, right? Go with 3 on the next one. Why didn't I write anything for that one?
It's 0.
So, 0, right? Remember, whenever we plug in 0, right, any term with the variable is now going to become 0. Now, you could have wrote it out. There's nothing wrong with that, but what I hope we get to is the fact that, hey, what's my constant term? If it's linear or polynomial, what's my constant term? Because everything else is going to go to 0. So if you need to see it, make sure you put it. But also start watching for that. That, hey, we like plugging in 0 because anywhere you had an X, that term, not the whole thing, but that term will become 0. Okay, so take that in mind. Now, is there anything wrong with the last one? This is another wonderful thing about dealing with functions. We can go change the perspective of what we're working with. This quadratic might have a connection to some problem as far as application is concerned. And let's use t for time instead of x. So that way the t is more meaningful for what I'm doing. Right? And what we find here is if I go plug this in, what is it that I can do now, or what is it the only thing I can do? And all you could do is simplify that, right? Before we were able to evaluate. But when you get here, all you can do is simplify to say, hey, g of t equals t squared minus 7t plus 3, which guess what? Isn't that the same thing we just had? The difference is the perspective, right? Any concerns with getting to these values or results?
When you square the 5 with 125.
All right. All right, so I think we only have time for one more, so let's look at this one. Now, what I want you to see here is I gave us another quadratic. Down here, I have it factored out for a reason. When we start solving equations, one of the things that we'll do is take our function and say, hey, what if this function is equal to 0? Well, we can create an equation that says x minus 2, x minus 4 equals to 0. Just remember that at that point, set the factors equal to 0 to solve. Well, guess what? If it's equal to 0, that means our y value is 0, and we just found some ordered pair solutions. So the context in how we describe our solutions is going to change a little bit because they're now only with ordered pairs. So keep that in mind. Now, as I go through and deal with this graph, though, what you're going to find is it'll look something like this. We know it's quadratic, so hopefully you're expecting that U shape. That's what our graph's going to look like. Okay. Now, what happens here is we've already talked about quadratics, which is why I wanted to start with this one. And to show you that sometimes we plug stuff in for a particular reason. Right? There's a test that's taking place here. And as you can see here at the top, I said, let's check for symmetry. Now, does a quadratic have symmetry? Yes. The difference here is when we start talking about symmetry, the symmetry that we're going to refer to when we do this test is going to be symmetrical to the y-axis, the origin, or neither of those. Okay, so these are very particular situations. So make sure you see here that, hey, as I look at this graph, and as we talked about it, we can kind of talk about there being symmetry. But make sure we take this and compare it to what we're about to see. Is everyone clear on that? Now, symmetry to the y-axis means that it's going to be lined up where both sides of the y-axis are exactly the same. Is that the case right now? Is my graph exactly the same on the left side of the y-axis as it is the right side? So if I fold this over here, this is exactly the same as that.
Oh,
No, it's not, right? The symmetry here actually goes through what number? 3, right? So this symmetry is not going to be true in our case that we're looking at right now, okay? So this is very specific, is the key that I want to talk to, right? We talk about symmetry, but there's some special cases that are helpful. If you have a function that's symmetrical, you can use that to your advantage, okay? Now, with that said, though, the way that we test for y-axis symmetry or symmetrical to the origin, and I'll make sure to show graphs to help with this, is we plug in negative x into our function. Just remember here, all we can do is simplify. All right. With that said, then negative x times negative x is positive x squared. Negative 6 times negative x is positive 6x. And then just bring down that 8. Now, what happens here, if it was symmetrical, we should be able to compare it back to what we deal with. So right now, is the function I just found the same thing as what we started?
no.
No, because it went from negative 6x to positive six x. So we would say here that like, hey, g of negative x does not equal g of x. So the next thing to try is let's factor out a negative off of everything to see if it helps. Okay, so we're gonna rewrite this statement with a -1 times, and they go through and change all three signs. Now, with that same comparison, we were just looking at that trinomial. And we want to see if this trinomial matched up with what we had up here. So does this one match my original function? Even more so, right? Like all the signs are kind of messed up now, right? More signs are. So again, what we find here is that g of negative x does not equal negative g of x. So this has no y-axis or symmetry to the origin. So it's not symmetrical to the origin or y-axis. That's how we would interpret it. Now, the reason I wanted to start with this one is just to make sure we see that we've already talked about quadratics kind of having some symmetry there, right? The big difference is here is make sure we go back and see that my specific situations are for the y-axis and the origin. Okay. Now we'll make sure to look at some other ones with this. As I said, it's definitely helpful. When we get to our third module, that's where we're going to start to see a lot of this help us out. Sorry, thinking like say polynomials and stuff. Okay. Now, what I want you to take from this problem though is plug in the negative x and simplifying. That's the one thing to take from it today. With that said, though, be prepared to start using the results you have for purposes like just comparing back. Did I get the same function I started with? Did I not? If factor out the negative helps. Not right. That's kind of some things we can take from it. Tomorrow we're going to plug in some other stuff. All right. Well, you'll see this is where we're going to go back to the average rate of change a little bit. Okay. That's what we're going to be dealing with tomorrow. So have a good day, and I will see you tomorrow.